Afternoon. Marianne is a senior scientist at LBNL, and she's also the director of the Building Technology and Urban Systems Division. We have a hierarchy, as most places do, in that Building Technology and Urban Systems Division is located in the energy technology area at LBNL. Marianne oversees a variety of building energy research activities, mostly supported by the US Department of Energy. And she's also the director of the Demand Response Research Center, also at the lab. Her work involves developing and evaluating new technology and building components, such as windows, controls, operations, simulation, whole building and electric load shape analysis, and building behavior in general. Her division also conducts research in the data center energy efficiency area, industrial energy efficiency, and federal energy management. She has authored over 90 peer-reviewed publications related to energy efficiency and demand response, and has worked at LBNL since 1983. She's a board member of the American Council for an Energy Efficient Economy, and also a board member of the Open ADR Alliance. She has a master's degree in mechanical engineering from UC Berkeley and a licentiate from building services engineering from the Chalmers University of Technology in Sweden. So I'm sure all of you will join me in welcoming Marianne to talk about, now it's going to be different than demand response. It's demand flexibility now. Marianne?
Thanks so much, Janie. So before I bring up my PowerPoint, I'm just going to make a couple of comments. Thanking Janie again for her service. Janie is retiring this week, and it's a pleasure to have her helping moderate my session today and introduce me. She's been a phenomenal partner in our demand response research and other things at LBL. And I also want to talk a little about the building behind me. I picked this background. I have one picture of FlexLab in the talk, but so I sort of get started on it. We are working on grid interactive efficient buildings, which is the title of my talk. And this facility is a set of side-by-side test beds. You'll see they are in pairs. So here, this one over here, those are a two-story one and some single-story ones. And then over here is a rotating test bed. So we can actually change the way the building sits and change the way the sun hits the windows. So we're very fortunate to have these technologies. And when we do research in technology, we're looking at both the energy efficiency, so how to make the building use less energy, but also this new area of demand response, which I'll talk about. So let me share my screen here, get my PowerPoint up for you. Okay, Janie, can you see my screen here?
Yes, most definitely.
Okay, so this title is the Grid Interactive Efficient Buildings and Automated Demand Response. And the GEB title is the title that the US Department of Energy has been using for research in this topic. And I'll talk about demand response and how that relates to demand flexibility. And Janie, will you give me a sort of a 5-minute warning or a 10-minute warning? Actually, let's do 10. So I stop and we start having more open discussion.
Certainly. I'll turn my video on at 10 minutes before your close time.
Great. So this is the title of my talk, as I mentioned, and I am the Division Director of the Building Technology and Urban Systems Division. I am going to give you an introduction into the energy technologies area at LBNL first, and then I'll talk about why we need demand flexibility for a low carbon grid. So in a lot of today's presentations, we've been talking about transitioning to a low greenhouse gas energy world, and this technology is important for that. I'll talk about what it is and then how we get it. So that's really the main core of my presentation. But I want to talk for a few minutes about this picture. And this picture shows you a variety of technologies, basically two kinds, supply side and demand side. And we are changing the way we generate energy. And so we need to change the way we consume energy. And as we look across these types of technologies, you'll see one of them that kind of is different is storage. So there's a lot of new technology around storage. And historically, Lawrence Berkeley National Lab has done a lot of work on batteries, a lot of early work on lithium ion and other battery chemistries. But you'll see there's a lot of systems issues here as well, like integrated systems and transportation and the electric grid. So we work on a variety of technologies, which I'll go through into more detail. But the primary theme of this talk is the concept that we're going to cleaner local energy systems. So historically, we build large power plants, and we have a base load, and we have a dynamic load that follows the load with peaking turbines and things like that. But when we move to something like photovoltaics and wind, we want to have the generation as close as possible to the use. Now that's a challenge, of course, in cities. You're not going to put in big wind turbines, and the number of photovoltaics on the roof is not enough to power the cities in many cases, but it can certainly help. So we want cleaner energy. So when we think about grid interactive efficient buildings, the first place we start, and the area we've been working on for many years, is the individual components. Making a better window, making better plug loads, improving the efficiency of HVAC, creating LED lighting and controls, and understanding the component technologies. We still do a lot of that work. If we make a better window with a good solar heat gain coefficient, we can reduce the need for cooling. So one of the first things you do, with many of you know, in energy efficient buildings is make sure that you have a good facade, good insulation, and a good window, because that reduces the size of the heating and cooling that you need. That is going to continue to be a priority. And there's been a lot of talk about electrification and putting in heat pumps, but we still want that efficient building. So we have to put in, we don't need as much heating and cooling. And measuring the plug loads, we want to have plug loads where we can measure the power in every plug in the house. So as we move from components, our next step is integrating them into building systems. And here's a picture of a whole building where we have communication and control at the whole building level. And you heard a little bit about the control system description language. That's very helpful for something like model predictive control, where we actually may have energy use as part of the sequence of operations. So we want to move from efficient components to integrated building systems. And finally, it's very important that those building systems be integrated with the grid. So we want components, whole building systems, and then grid interactive efficient buildings. And I want to make sure that we also acknowledge the role of transportation and electric vehicles in part of that system. So that's the concept of the grid interactive building is to make sure that there's communication with the grid. Now, why do we need this? This is the famous duck curve from it was actually in 2013, I think it was first developed. And this is a duck curve that's been around for many years now. The reason it's called the duck curve is the shape of the duck. The belly of the duck is getting deeper. And so what you'll see on the y-axis is hours of the day, and on the x-axis are megawatts. And I'll talk a little about units in a moment. This duck, the head peaks at about 25 gigawatts or 25,000 megawatts, and the belly's down at 11,000. We're going to come back to some of these ducks in my talk. But as you use more renewable solar, this duck belly gets deeper. There are different shapes around the country. Some parts of the country, in Vermont, they call it the alligator. Sometimes we call it the hummingbird. And you basically want to flatten this guy because we want load to use more electricity around the middle of the day. And that is very different than what we've been doing. It used to be with time of use rates, the cheapest price would be at night. But now we're looking at the cheapest price being in the middle of the day when there's plenty of renewables. And we want to soak up that low cost, clean electricity. We don't quite have those tariffs yet, but SoCal Edison was thinking of matinee pricing, or even free electricity in the middle of the day. But that's the best time to charge your EV. It's the best time to charge that heat pump water heater. It may be something that thermal storage could do. So it's a very important piece of our need for demand flexibility. That ramp late in the day, that's very hard for the power plants to go from 19 gigawatts up to 25 gigawatts in only 2 to 3 hours. So that's one of the challenges as well. Let me make sure we get a little grounded in the units that I'm talking about. We all understand what a watt is. A LED watt is a 10 watts. A lamp, an incandescent lamp used to read around 60 or even 100 watts. A home typically uses a couple of kilowatts, maybe up to 6, peaking. Those are the peak times. Large buildings can use about a megawatt. And the state of California uses about 50 gigawatts. So we have 1 watt, 10 to the 3 watts, 10 to the 6 watts, and 10 to the 9 watts. And when you're teaching, those are really important units to get the students oriented around these factors of 1,000 that move us from watts to kilowatts to megawatts and gigawatts. So I'm now going to share with you a little more about the concept of the duck. This is a spring day in 2019. This is an actual day. And on the left-hand side is those gigawatts. So you'll see this is similar to what I showed you, where in the middle of the day, that red is curtailment. So we actually could not use all the electricity. We actually were spilling it. It's not just the shape, but we actually have curtailment. So we're not able to soak up all that electricity that we generated. And we're typically curtailing about 5 gigawatts. So that's a typical spring day. Now, spring in California, there's not a lot of cooling load. There's a lot of sun, and there may even be hydro. So you'll see the colors. I have the purple magenta there is the nuclear base load. This is for California. The green is the large hydro, and the large hydro is very available in the spring. So that varies. If we have a drought year, you'll see the thermal. Those are gas power plants. Imports. So we get some electricity from the Northwest. The green are the renewables. And the very top is the shape of the load. And then that red is the curtailment. Now, what is remarkable is on Memorial Day of that year, we actually had 40 gigawatt hours of curtailment that we couldn't even use. That was the highest we've ever reached in California. 2020, we were already in the pandemic. So the extreme duck of 2019 shows us that we need to do something to improve our ability to use the solar that we get. So if we don't address this problem, we're putting up more renewables, but we're not using them as effectively and efficiently as we should. So that's one of our challenges. This is a low demand, a sunny day. So we got the solar with less exports in the middle of the day there. And we had 40 gigawatt hours that we could not actually soak up. Now I'm going to share with you a little about the carbon savings by time of day. There is a company called WattTime that will send you a signal, and you can follow the signal to get your building to use the cleanest electricity during the day. So here I have different seasons, and on the y-axis is tons of CO2 per megawatt hour, and on the x-axis there is time of day. So you can see in the middle of the day, so the marginal emissions are the average emissions, and then anytime we're below that 0.3 value, we're cleaner than normal. And if we're above that flat line, we're dirtier. So we want to use more in the middle of the day, as I had showed you. And there's a couple of shapes during the day and season. And even if we could shift loads seasonally, so some industrial processes may be able to consume more seasonally or do storage seasonally. But the basic idea here is that we want to use as much electricity as we can when it's clean and avoid using it when it's dirtiest. And it's dirtiest around dinner time. And that's quite a challenge for us. Now, this graph shows you the motivation for demand flexibility. I originally wrote this for demand response. Now, demand response tends to be the concept that on a hot summer day, say the 10 hottest days of the year, we might have grid congestion. This is all related to the way the electric system is sized and whether the buildings are causing a low resource adequacy or there's plenty of resource adequacy. So historically, and I'll get to this in a moment, the concept of shedding demand on a hot summer day is what we call demand response, whereas demand flexibility is more the desire to do things like this and make the load more flexible during every hour of the year. So that's the difference between demand response and demand flexibility. And some people will say demand response is a program, demand flexibility is a capability. So we want demand flexible buildings. Here's some reasons why we need that demand flexibility. We want the grid to be more reliable. So if there are congestion issues, we want load to be flexible. We want the system to be more economic. Those congestion days where where the grid is constrained, that's more expensive. And then the congestion itself, we may have some areas of your state are congested and they need to do a distribution system upgrade. And other areas, there's plenty of capacity. The areas where we're in a distribution upgrade, if they can do demand flexibility and demand response, they can manage the peak load so they can wait another 5 or 10 years to add capacity to a region. And then the intermittent resources, that bottom one under objectives is the reason to improve our use of electricity when it's cleanest and have low carbon operational performance. If we are going to have demand response and demand flexibility, we need to schedule the load and we need to let the load know what we want it to do. The best way to do that is with electricity prices, and I'll talk a little about that later. Ideally, this is automated. Now you can historically send people a time of use signal. You could text it to them, or you could say, always, here in California now, between 5 and 9, the price is higher. It used to be the highest between 2 and 6 in the afternoon and then cheaper at night. So these tariffs are changing as we have more renewables on the grid. And in the final column of control strategies, I want to make sure that we're thinking about the way we configure the automation. Is the communication going straight to the refrigerator, or is it going to a gateway of some sort that's talking to a number of other things, or is it in the cloud? And so there's a lot of different architectures as we think about how to move from today's technology to what kind of automation we might want and which devices in the home or in the large building are best suited or oriented towards receiving these signals. So those are some of the basics that we're going to get into. In this graph, I'm going to talk about the different kinds of services.
Marianne, I'm going to interrupt just a moment. We had a question that might be a clarifying question that might help some people not be stuck here. And that is, when you do curtail power, how is the energy absorbed or dissipated off the grid? And I think you're about to answer that, but I just want to make sure that we capture this possibly sticking point.
So say it again, Janie.
Sure. It's how, when you are going to curtail power, how is that energy absorbed or dissipated off the grid? In other words, the power is there. They're assuming that there's going to be a demand for it, and you curtail the demand. So what happens?
Right. So the most common thing we do are change set points of air conditioners or heat pumps. And air conditioners are the most common source. So you might turn the air conditioner off or change a set point, and I will get into some of those details. So this figure shows you a little bit about what we're going to get into. On the top left, we have the shape of electricity prices. And if we can get the building to change the way it uses electricity to try to save money, that's also good for the grid in many cases. So in this particular example, the middle of the day is a super off-peak rate. That peak period that's red is the high price time. So if you can get your building to change its electricity use, that's good for the grid because those prices are based on congestion. So the peak price now, because of that duck curve, the price is most expensive in California between 5 and 9. And around the country, we're putting in the hourly meters and moving towards some sort of demand flexible pricing. On the second to the right, the very top right is the shedding, demand peak shedding. And this is the traditional demand response where you will change the way you operate maybe for 4 hours. And I'll go through some examples of that. On the bottom left is the new type of response that we're looking. It might be in response to a price or some sort of signal, and it's shifting load. So pre-cooling the building is a form of shifting load. Say the high price is at 2 o'clock in the afternoon, you may pre-cool from noon to 2. Or if the high price is from 5 o'clock and you're coming home to a hot house, if you had pre-cooled the building from 3 to 5, you might be able to use less of that expensive electricity. And we are also looking at how different kinds of energy storage, whether it be ice or chill water or phase change materials that are distributed in the walls, or other kinds of technologies might facilitate that, or electric batteries. So some companies put in solar photovoltaics and give you a battery. And then that last bottom one on the right is what we call shimmy. Now, the reason we called it shimmy is because we were looking for a verb. These are shape, shift, shed, and shimmy. And we are shimmying the load, and we are allowing the load to follow some sort of faster signal, like a regulation signal that can help for voltage or frequency, or follow the load, or ramping. And some loads like VFDs can provide these shimmy services, and they can actually be energy neutral. And that's what that dashed line is showing, that the load might go up and down and follow some sort of advanced demand response signal, demand flexibility signal. So we use these terms shape, shift, shed, and shimmy to help people remember the different kinds of services. And we've been modeling the capability of these loads to provide shape, shift, shed, and shimmy. Now this graph shows you, again, that duck curve shape is that white line. Now remember, the white line is actually the total load at the top minus the renewables. So the total load at the top is the load that we're trying to make flexible. So the net load is the total demand side load minus the renewables. And that gives us that shape of the net load curve duck. You'll see that I have process pumping, refrigeration, pool pumping, EV charging, HVAC. And in the table there are the key loads that we've been modeling for the state of California to try to understand how much demand flexibility is available in different end uses. So in homes, in commercial buildings, and industrial. So in homes, the most common thing that we do is change the air conditioner. And I'll go through the technologies in a moment that do that. But we have pool pumps and we have EV charging. Now, space heating and water heating in most of California is gas. But as you've been hearing, there's a huge interest in electrification. And if we're going to retrofit our water heaters and our heating systems to be all electric, we're going to want to have heat pumps. But we need to make sure those heat pumps are providing flexible load, or they will make the duck curve worse. Those heat pumps are going to come on in the morning, and they're going to come on around dinner time, and it'll make the duck steeper. So we have to make sure we have flexible electrification. And we also want to continue to enable and automate the capability of many of these other loads to provide flexibility, like the industrial process as well. So we've been modeling the capability of these loads at what scale, and the picture in the blue there is the average load shape, and which of those loads we consider to be flexible. Now here's a picture of some of the unused technologies. Smart thermostats are one of the most common, and some utilities are offering a bring your own thermostat program. And if you bring a smart thermostat, now many of these smart thermostats, we know them for energy efficiency. So they'll learn your schedules, and they'll turn things on and off. But many of them can pre-cool the building and help in load shedding. And so they'll receive a rush hour reward signal and be able to actually change the set point for demand response programs. I have a picture of a ballast there, buildings, industrial, warehouses, data centers, EVs, variable frequency drives and water pumping. So there are a variety of kinds of technologies that we are evaluating both in the field and in models to help understand their capability in responding to the duct curve and other demand flexibility needs. So we need to be able to shift load to enable more renewables. The graphic there, it's a little bit hard to read, but in blue, under this graphic here, is the current participating load. And the orange is technologically available resource. And then the green is the max available. So we've been modeling, if the capability exists in the stock, then we have to figure out what incentives are necessary to get the retrofit of the controls into homes. So this technology is expensive, and we, some of these thermostats and controls are not free. So we look at how much does it cost to be able to install automation, and we are modeling customer participation. So that's part of what we do in these models. And some of you heard Margaret Torn's talk this morning, where she talked about the capability of transforming buildings and the energy efficiency and heat pumps that we could have by 2050. Well, that assumes we're going to go out and retrofit and recruit customers to participate. So that's a very important part of our research, is understanding what's in homes today, what's in large buildings today, and what motivates a customer to participate in a heat pump retrofit. And then, as I said, if you put that heat pump in, you want it to be able to receive some sort of grid signal, because it will make the problem worse if we don't. Now, on the right there is a picture that shows the DR shift dispatch of gigawatts and the hour of day. And some of these things can go twice a day. And many people tell me this, and I know this, that you may use your water heater in the morning for showers, and you may use your water heater around dinner time for washing dishes. And in fact, because of the duct curve, so that black line is the inverse of the duct, and that's the shape that we want load to be the inverse of the duct. And we look at when we want the load to be doing something different than it has been doing, and those are the shift capabilities. And some of the loads can shift twice a day. So we want to be able to see and control our electricity use. And this picture here shows a refrigerator, a washing machine, a water heater, a home energy management system, an air conditioner, a utility meter, and photovoltaics and batteries. And the real goal is to actually make these things into systems. If you buy a BMW EV and a Tesla Powerwall and a Nest Smart Thermostat, those things don't talk together. And that's one of the challenges as we think about changing these load shapes, is doing it as in a system perspective. So that's one of our challenges in the research that we're doing to try to improve the ability of buildings to be integrated with the grid. So there's a couple of standards that I want to mention that you're going to be hearing more about in the coming years. One of them is IEEE 2030.5, which I'll talk about in a moment. The second one is OpenADR 2.0 A or B, and the third one is CTA 2045. SEP2 was primarily taken up in communicating with photovoltaics and inverters, although it has the capability to also interact with building technologies. And it has a price mechanism where you can send prices to devices. OpenADR is something that we started at LBL back in 2001, been working on it for almost 20 years. It is a client server architecture. And so the picture there is there's a server at the utility, and the utility sends messages to the buildings, and they're using OpenADR. On the very bottom is what's called a pricing data model. So OpenADR is what's called an application layer model, and it puts a price signal or a demand response flexibility signal into a machine readable format. It's sent over the internet, and the building is pre-programmed to respond. And I'll give you some examples in a moment about kinds of responses that a building can do. But the control system is pre-programmed to be listening to the signal, and it's listening 24 hours a day, 87, 60 hours. And that technology has been very successful and is deployed around the world. It's used in China, it's used in Australia, it's used in Europe, and we're very active doing research to understand how to make it cheaper to deploy that kind of technology. Now, CTA 2045 is a dongle, a port that has both a physical element as well as a software element. So a CTA 2045 heat pump water heater has the ability to receive signals, and those signals can come from a utility or from an aggregator. It can actually receive an OpenADR signal or an SCP signal, and it's both a combination of hardware and software. So we have hardware and software interoperability technologies to help us start to allow these tech buildings to be able to receive these signals. I'm going to give you a little bit of an overview of the kinds of things that buildings can do. And here on the left is a picture of a building in Martinez. It's a 100,000 square foot office building. The red line is the typical day electric load shape, and the blue line is the way we operated it with what we call global temperature adjustment, which I'll describe in a moment. And then the pink line is the negawatts on the bottom. So you say, what did it look like on a typical day? And then we reset the thermostat twice. So typically you go from say the building's running at 70, you might go from 70 to 75 or 74, and the VAV boxes go to minimum and the chiller's back off. And we get some shed because we're running the building at a warmer temperature for a couple of hours. Depending on how the commissioning is, it may perform well. Sometimes you pre-cool and you get the mass to be cooled down so people don't even notice it. Some buildings are already too cold and people are more comfortable when you try things. So the list here of buildings shows you all the types of buildings we've worked with: office, IKEA, Target, Walmart, office buildings, data centers, and schools. Most of them do that global temperature adjustment, but the table shows you other things people have done, like supplier temperature reset, VFD limiting. And we had our very first industrial part, the Sven Hart's Bakery there. They actually bought extra pans and they turned off the dishwasher. So they choose what to do. These were all fully automated. We installed a gateway box with OpenADR, and we used the existing control system to program strategies to allow the building to change the sequence of operations during the demand response events. Now, if you were going to do this for demand flexibility, you might receive an hourly electricity price and continuously move the set point. Say when the price is cheap, you might pre-cool. And if you know it's going to be warm at 3 o'clock, you might change the way the building's operating at those times. So I'm going to go to the next slide. I've just got a couple more to finish up. This is what the integrated test systems look like. When we want to identify the technologies, we create these supply curves of what's available. So I have the colors there on the left show how much is available in California for an average shift event. I won't have time to go through all the details, but we model the capability of HVAC and EVs and pumping, and how many gigawatt hours we can provide at a particular cost per kilowatt hour. So we look at how much it costs to install it and then the lifetime of the measures. I show a picture of FlexLab here. That's one of our test beds where we're testing demand flexibility. And then in our new EPIC project for the state of California, we're actually going to be using model predictive control to pre-cool the building and use heat pumps and kind of move electric loads around to create low carbon operational strategies. Janie, how much time do I have left?
Hi, Marianne, you have about 12 minutes.
Okay, so I'll spend a few minutes on this one. The state of California is in the process of developing a price communication system. And I've been talking about the IEEE 2030.5, the CTA 2045, OpenADR. The concept is to use those kinds of technologies as well as the watt time signal, and to create the ability for the utilities in California to use price signals as a way to send demand flexibility messages to buildings. So the state and Lawrence Berkeley Lab and the utilities are collaborating on creating a price communication system. The all electric tariffs would be sent to buildings in a digital form. And you would be able to control your building to save money as well as to reduce the carbon footprint. And you'll see there's a public broadcast system. So the concept is we would actually not only offer internet signals, but FM broadcast. And FM broadcast has been tested. PG&E is currently testing the capability to send FM signals to electric resistance water heaters and to have the water heaters change the way they operate during times when the electricity prices are high. So there's a list there of smart plugs and thermostats and batteries and water heaters. And we want price responsive and greenhouse gas responsive devices. So not only are we planning to send electricity signals, we also want to use that watt time signal to send a GHG signal. If you sent a GHG signal, it may not be directly paired with the tariff, but might you be willing to pay a little bit more money if you knew your building was operating as clean as possible? So that we do know that some customers are happy to do that and pay a little bit more and save on carbon and improve their ability to integrate with renewables. So that's an important part of what we're doing as well, is thinking about the technology and the way we're structuring this automation. We could also send those signals to batteries, and we are looking across the demand side systems, industrial buildings, EVs, and we don't want to just send them to devices. We want to send them to a whole building control. So a smart home energy management system would ideally know something about some of your biggest loads and be able to manage them. So this is my final slide. I want to reiterate that part of the challenge in getting to a clean energy future is making sure that demand side systems are part of the smart grid as we try to electrify loads and have more renewables. As you have more intermittent, variable, renewable supply, you need more flexible demand. And that requires us to move from static energy efficiency to dynamic energy management. That also requires a lot of communication and control. So we're going to be having more data on the health metrics that we talked about, the electricity use of devices, the temperature in the building, and the EV charging schedules, considering the building as a group of buildings, looking at a microgrid, and campus levels where you may have groups of buildings that are controlled at a community scale with batteries and photovoltaics that are integrated locally with some sort of renewable technology. So we need to enable automation to help with both energy efficiency and demand flexibility. And we're looking forward to collaborating with the BEST Center and a lot of you in the future as we try to deploy these technologies and make sure we're able to do this in a cost-effective way to enable more renewables on the grid. I'll stop there and answer questions.
Thank you, Mary Ann. And I'm sure you would hear the applause if we could have applause happening here. We do have some questions for you. There's a note that it looks like there's competing drivers here. There is sort of there's certainly the price that has been sort of a pass through. The cost of producing energy at a certain time will be X, and you can pass that through, versus the carbon, a price that would reflect carbon issues. And so I think that's just a comment. We have a question here that the person asked the question and then pulled it back a little bit, but I think it's worth asking. And that is whether there are any candidates for allowing devices to communicate with each other and a central hub that would allow consumers to guide the priorities of load control, such as an X10 or Insteon or some other broad range of devices. I think you sort of covered that with OpenADR, but let's see if
yeah. So the X10, of course, is power line carrier technology, and I have some X10 in my home, and I've also got some Lutron. You know, we got Bluetooth, we have Wi-Fi, we have Z-Wave, we have Zigbee. So there are a lot of physical air communication systems. As everyone knows, the problem is if you have an old refrigerator or an old washing machine, they're not able to talk. But there is a collaboration between Google and Amazon and Apple to look at interoperability in homes. And one of the problems is how open will it be? And, you know, joining some sort of alliance. Of course, in commercial buildings, we have BACnet. So there are wireless and wired kinds of control and communication systems, but it is absolutely a big issue for us. So I do think that there's a lot of work needed in trying to improve interoperability. One issue is getting the signal from the electric utility to the building. And then the second is, what does the building do with it himself? That's areas we both need more work on. Getting the signal is that 2030.5, OpenADR, and CTA. And then within the building, we need more interoperability.
Thank you. The next question is, hang on, the timing is bad.
Don't worry about it, Janie.
Sorry about that. What attention is being paid to the use of solar thermal, such as solar hot water and ice storage, in terms of decreasing the amount of load on the grid? We know it's viable and can reduce the need for electric or fossil fuel loads by as much as 80% for domestic hot water and space heating and cooling. So
yeah, no, my first job in college was actually with a solar thermal company, solar hot water, solar swimming pools. I think we need more of that. It's amazing how little is done in that area. There's also combined photovoltaic with thermal, and those are really interesting. But it's a good question. I think we need more of that. So was there a second answer? A question about thermal storage?
Just a question about how they can be used and what, if there's any limitations to those.
It's first cost. I mean, we really need to get low cost storage integrated with HVAC.
I don't have any further questions. I do have a comment that one of the people listening thought that Apple and Google would be an interesting merger. So that,
yeah, powerhouses.
Yes.
So let me I think there was a comment, Janie, about prices, electricity prices.
Right, versus something communicating carbon issues, yes, whether those can be coordinated.
Exactly. So one of the challenges is utilities are slow in adopting dynamic prices, right? And the tariffs don't always reflect system conditions. That's the issue. And for example, right now, the critical peak price program that PG&E has in California, the peak price is still 2 to 6, even though the peak is 5 to 9. But the tariff, it takes a lot of regulatory activities to change the tariff. So the tariffs lag the grid. And that's one of our challenges, is moving towards variable pricing that is more dynamic. And that's one of the reasons the state is trying to create this dynamic price server with a view towards moving towards real-time pricing and transactive energy pricing that reflects system conditions and carbon. So you're going to see a lot of innovation in that space in the next 5 to 10 years.
That may be the question. This question may be exactly what you just answered, but if you want to add a little bit to it, someone has asked how market drivers and technology drivers interact.
So one of the things that question doesn't mention is the regulatory goals. And the state of California has very aggressive carbon reduction goals. The number one thing the state of California, as an example, should do to reduce carbon is electrify transportation. The second thing is to electrify heating and cooling. I mean, cooling, heating and water heating in buildings. So you know, again, Margaret Torn mentioned it this morning about electrification. So is that a market driver or a technology driver? I think adoption is lagging the technology. So we know we have to have technicians that understand heat pumps in parts of the country that don't currently have heat pumps. You know, I know neighbors that have tried to put heat pumps in. It's very difficult to find the service technicians that know how to design and install and operate heat pumps in certain parts of the country. So you're going to see a lot of need for training related to heat pumps, and that there's at the top level is the policy goal of reducing our carbon footprint, and then we have markets evolving and technologies evolving, and we need customer adoption.
Yes. I think that's the questions that we have for now, but are you willing to go to the Meet the Speaker space after this? If
I can go for a few minutes. I don't know how to get to it. Do I go
okay. So if anyone wants to go to the Meet the Speaker space and have a small chat with Marianne, that's possible. You go back to the main menu
forum,
and over on the bar there towards, I don't know if this is coming across the correct way, but towards the right-hand side, there's a chat, and the chat should open up and give you the option to get into the Meet the Speaker space.
Okay.
So
I'll be able to go just for a few minutes.
Great. Thank you so very much.
Thank you. Thanks, everybody. Thanks for attending. Bye.